Minasan konnichiwa. I'm Adam, and yes, as just mentioned, I'm from Trelleborg. So today I'm going to be talking on how we are bringing nanocomposites to the scale and realizing the true potential of them from renewables to healthcare. Okay, so we're just going to go through this really quickly. We're going to have a brief overview of who Trelleborg are, for those of you who don't know them, products that we do, and then we're going to look delve down into one which we enhance using carbon nanotubes, a product range we called Frame, before looking finally at future product development. Okay, so Trelleborg. It's probably the biggest company you've never heard of if you haven't, because they are founded in 1905, over 100 years old. They have a $4 billion turnover, and they operate globally across the world. Now, they use this to basically bring products from space to seabed, as they like to say. So in the satellites, into airplanes, and all the way down into the deep sea submarines. Okay, so just some of the products that we do. We basically respond to the complex industry demands that we are seeing develop in today's society. So demands such as increased longevity. So what we're doing at Trelleborg is we're improving the aging using single-wood carbon nanotubes. So specifically, we see hydrolysis-resistant, tear-resistant materials. Also, we are looking at improving recyclability by mixing these into thermoplastics. So obviously, as mentioned in the previous talk, then the generation 1 is the thermoset nanocomposites, but obviously they're not recyclable. So we're looking at using thermoplastics to try and open up new recycling pathways, something which is obviously very big on everyone's minds in today's society. Thirdly, we're also looking at complying with stringent anti-static regulations, so such as meeting fire certifications and those which might be going underground in mines to try and get the explosive certifications. Also, an interesting one is the viscosity of the polymers. So obviously, trying to get the volume up, so we're increasingly in today's day and age, we're trying to get more and pay less for it. So one of the best ways of doing this is by high throughput manufacture, but obviously if we're putting tons and tons of carbon black into a material, it gets very viscous and quite hard to deal with. But by using such amazing materials such as the tubal, we can get very good conductivity at incredibly low weight loadings, which then means it's easier to process. Better wear resistance, we're also seeing an increase in the abrasion resistance of the materials using that. And finally, again, all of this feeds into that mentality at the moment of we're trying to essentially make the same products last longer and get more for our bang for our buck. So superior tensile strength, we can see staged improvements depending on how they're mixed into the polymer. Okay, so that's how we're responding to the industry at the moment, and these are some exact actual examples. So we're making mining mats, we're making squeegees, we're making medical textiles with static dissipative properties. We are also making radar-absorbed materials, so this is what I'll be talking on in a second, the Frame product range. But we also do absorption in noise and vibration as well. So that's either in light rail boots, so trams that go around city centres. You don't want, you're sitting at the opera, you don't want a little rumbling tram going by, or indeed if you're living in a highly built-up area, you don't want all your chinaware falling off of the shelves every time a train goes past. So they put down these boots to basically dampen that. We also make leading-edge erosion strips that go into aerospace, and we generally have a coating department which looks at highly functionalized coatings. We also operate in the offshore industry, so cable protection is one of the biggest areas which we do here, so bend control solutions, clamping solutions, but also in the floating offshore wind sector. So in Japan, I know certainly that your offshore wind industry is just starting to get off the ground, and one of the ways you're innovating here is using floating wind platforms, and also we see there across the world. Okay, so now this is really where the tubal comes into it. So this is the carbon nanotube enhanced product. We call it Frame, so that stands for Fully Radar Attenuating Materials and Equipment. Now, this is going into wind turbines. Why might it go into wind turbines, I hear you ask? So essentially, when you have a wind turbine out there rotating round and round these big blades and a big metallic tower, they cause this, no they don't, they cause this clutter on the radar screen, which essentially can look very much like storms, or they could look like aircraft. So if we take this bottom radar plot here, the wind turbines are within this white section, but you see all of this radar noise is coming from these rotating blades, which are essentially chopping up the radar and throwing it back to look as if it's actually taking up tens of nautical miles. So if you have a plane that you're trying to fly through here, you're going to lose its tracking as it does so. And of course, this is very important because you're needing to track planes both in terms of civilian and military cases. So this is such a large problem that actually in the UK alone, over 90% of the megawatt capacity of all wind farm applications last year were objected to on these grounds. So about 50% of these then had mitigation strategies that they worked through with the radar operators, like building new radar, but essentially that still leaves about 2 gigawatts of renewable energy that's blocked due to this concern in 1 year alone. So current solutions to this, apart from obviously what we're presenting today, is there's one called blanking and infill. So we go back to this screen here. Essentially what you could do if you're a radar operator is just ignore this whole section. That kind of gets rid of the horrible looking plot, but obviously that's not very good if you're actually trying to track anything through that. Or what you could do is have a new radar. So let's say your radar's here. If you position one here, looking this way, you're then going to get round this problem. Now this costs tens of millions of pounds to do, and therefore isn't everyone's first choice, especially if you're only building 1 or 2 wind turbines there. So an emerging technology is stealth wind farms. So what this is essentially is you mute this noise, you bring down that radar cross-section, and essentially you end up with a much cleaner radar screen with high-fidelity radar observation. So that's essentially what we're trying to do. Now, the technology behind this is we realize that of everything, it's not the spinning blades, it's not the fact it's there at all, it's the large radar cross-section that's the problem. So if we can reduce this, we remove the clutter and solve this problem entirely. Now, in order to reduce it, what we're doing is we're putting single-wood carbon nanotubes and making a nanocomposite, which essentially absorbs this radar, brings down this radar cross-section, and makes it much easier to track aircraft, track storms, etc. Now, the product range that we have absorbs over 99% of the incident radar wave, and it essentially, therefore, makes it stealthy. So what we have here is a graph for all of those data lovers out there, and essentially we're looking at the reflection graph of a sheet of metal. Okay, so up here in the 5+ gigahertz range, this is frequency on the x-axis. If it's at the top here, it means that 100% of the power that's been fired at that metal is being reflected back at the radar. That's bad. That means that you're going to see a lot of noise on the radar, and you're going to be unable to track your aircraft. Now, this dip here that we can see, around 2.7 to 2.9 gigahertz, is showing that it's absorbing over 99% of the radar waves, so you get a decibel reduction loss of over minus 20 decibels. This range here, coincidentally, is the S-band primary surveillance radar region. So that essentially is where you see in your civilian airports, their primary surveillance radar, so when people are flying into maybe Kansai International Airport or Tokyo, they're going to be scanning the skies using this frequency, tracking your aircraft through and making sure that everyone lands safe and sound. So, this here is, for all those non-data lovers out there, is a more pictorial representation of it. So we have here the metal sheet, and this is a portable radar being processed by a tablet. I have videos of this too. If anyone is interested, then you can come up to me afterwards and I'll show you them. And essentially what's happening is this is acting just like a miniaturized normal radar, firing out power at this metal sheet and receiving it, and then giving you a radar plot. So you can see this is essentially a nice example of the problem, because you see this is the metal sheet, but all of this here is this extraneous multipath scatter region, which basically is representing there. Now, on the left-hand side, this is it coated with the frame material, with the two-ball products in there. They're acting there to absorb the radar, and essentially, you can see that on low sensitivity, you have a completely blank radar screen. No, I haven't just turned it off, it is still on. And then on high sensitivity, you can see that you can actually get a position of the frame coated metal sheet, but you have a clear radar screen. So when an aircraft is flying through this region, it's going to be able to be tracked perfectly across that area. So, as you can maybe tell, obviously, we're looking at this from a renewables energy prospect, because there are literally gigawatts upon gigawatts of renewable energy power that could be unlocked by using this kind of technology. But obviously it has diverse product applications outside of there, so also in military, fairly obviously, but also in telecommunications. Incidentally, between 1 and 11 gigahertz is where Wi-Fi, 3G, 4G, and some 5G bands sit. Also in the automotive industry, and really anywhere that you want to pretty much meet electromagnetic interference regulations. So we can mold this to any size, any shape, and have complex geometries that meet the radio frequency emission standards in electronics and antennae. So just to finish off really on future product development. So that was just looking at one such area where we're using carbon nanotubes, but we're also looking at using them in making more abrasion-resistant mining mats. So again, we're trying to make these last longer. They're going through a lot of tough times, these mining mats, having to sift out all the aggregates, but we can make them abrasion-resistant so they last longer. We can also make wear-resistant squeegees, so these are used in screen printing. It's thousands of years old technology, but still used today to make your PCB on your iPhone. We also make durable light rail boots. We're looking at making this out of the carbon nanotubes, and tear-resistant leading-edge erosion strips for the aerospace industry, but also actually for renewables too. And essentially, we're just making high-strength, resilient polymer systems by using the carbon nanotubes available that we're seeing today. So just to end on a summary, we now are in the very lucky position, and a position which, when they first came out, maybe some people would never thought we'd get to, but single-walled nanotubes are now available on a large scale. They're commercially available. And essentially, that means we're able to now start transitioning out of just the prototypes that professors have in labs and research groups are looking at, and actually start making industrial manufacturing processes with this. And Trelleborg are exploring the full range of benefits available by using single-walled nanotubes to then bring this to the industry and ensure that we maintain our position as a world leader in engineered polymer systems. So the next step is, can we also do the same thing? Can we make commercially available functionalized single-walled nanotubes that are able to maybe interact stronger with the polymer systems, so we can start seeing this incredible improvement in tensile strength that you see when you have functionalized nanotubes, but on a more commercial scale. So just leaves me to say thank you, and any questions?
Adam, thank you so much.